Let me start recording this meeting. Okay. So this is the window that you're going to see in your PC when you join Teams and click on the Team IP312 in the General tab. Now, these are on the top, you have a series of things which you can click on. One of them is a class notebook. And if I click on the class notebook, I get a variety of things. In my screen, I would be able to see all of your class notebooks. So it would be easy for me to follow, and it would be easy for Arpita, who's your teaching assistant, to follow what you've been doing. Basically, this obviates the need for your turning in physical assignments. If I were to give you an assignment in class, you would have to turn in a sheet of paper in which you would write down whatever you have worked out, a problem set, let's say. Now, this doesn't have to be done. What you can do is to just upload whatever you have done onto this class notebook. Now, each one of you will have a class notebook and your names are listed here. I won't click on any one of those, but let me click on, you should be able to see what is called a content library. Now, this content library is something where I will have common material for all of you to use. So these are materials which all of you have available in your Teams web page. There is a getting started web page. I will quickly go to the one which says links to recent papers. Yesterday I told you that in 2018, 19, and 2020, many papers, 27 papers have been published, which have been very highly cited. So I have collected those sheets for you. And these, one of them can be, for example, your critical reading assignment, which I'm going to come to in a minute. But this sheet, if you click on that, you should be able to see, you should see an Excel sheet that is coming. And that Excel sheet, which I will bring to your screen now. So that Excel sheet has got a list of papers. So these are 27 papers, authors, titles, the journal, and so on and so forth. Okay, so you would be able to access all these. And if you have a VPN, you should be able to see all the journals directly. You should be able to see all the journals directly. So that is something that you can see. So in addition, there is a tab which is called Files. If I click on Files, I have again some material which I told you about. One is a screen which says how to do the critical reading assignment. This is a detailed list of how to do the assignment. So you should not have any difficulty in doing it. What I would suggest is, if you like one of the papers which are listed in that Excel sheet, fine. Otherwise, go to the journal website and like organometallics or Nature or Science, look for some interesting organometallics paper and start doing what I have listed for you here in this list. So this should not be very difficult for you. So that is one thing that I told you about. Now let me go back to where I was. Yes. So this is a class notebook. And in the class notebook, I told you that I have a content library. The content library is what you should also see. And you should be able to find more material. For example, here I have listed for you the class presentation. Whatever PPT that was shown to you yesterday is here as a PDF file. So you should be able to access that. So this is it for an introduction or an explanation of the teams. Most of the things are very obvious, but in case something is difficult for you, you could contact Arpita or you could contact me. Now, I wanted to say, make a comment about Pigeonhole Live. Pigeonhole Live is something that is that allows you to vote for a question. You can enter your own question, but you can also vote for the question. So, for example, all of you have, some of you have written saying that you were able to follow the lecture on the 5th of October. That's fine, but you don't have to write it out again. All you have to do is to click on this, and you should be able to. In my case, I have not created a profile first, but you should be able to just click on it and say you had the same experience. So what this obviates or removes is the fact that you don't have to keep typing in stuff. You have the same question as somebody else, or you have the same experience, you just vote for the same question. Okay, so that is the advantage of Pigeonhole discussion. I will leave this particular Pigeonhole here, but you could, I would create some more meaningful Pigeonhole assignments as time goes on. Okay, so in the assignments, I have also created 2 test assignments because this is the first time we are doing it. Arpita and I are testing out how it will be if we just give you a link to a Google form. Click on this link, go to the Google website and do the Google form that I have given you here. These are just test ones, but we'll give you some real assignments later. I also have installed Kahoot, and I think Kahoot will have 2 class tests today. I will see if, depending on the time, we will have these tests just to get us started. Okay, so this is something that we will do later on. So let me get back to the PowerPoint presentation. This is indeed a distraction for us to go back and forth, but it is a necessary evil. Here is the PowerPoint presentation. I hope you're able to see that now. And our semester is delayed by almost 2 months. We should have started out in August. We are starting in October. So we end in January 2021. So let me quickly tell you about the 18 electron rule. Yesterday, I mentioned that almost all organometallic compounds obey the 18 electron rule. The reason for this strict adherence to 18 electron rule will be dealt with later. But the origin of the 18 electron rule is really the Lewis perspective is what you need to have. If I have a main group element, I have NS plus NP. NP can accommodate 6 electrons, NS can accommodate 2 electrons. So a total of 8 electrons can be accommodated in the main group element. So that's the origin of the octet rule. That's the origin of the octet rule. When you come to a transition metal, then you have ND. plus n plus 1 s n plus 1 p. So this is the electronic configuration of a transition metal. If you have a 3D transition metal, it will be 3D, 4s, and 4p. So this is the configuration. So you can accommodate a total of 10 electrons in the d orbitals. So if I have 10 electrons in the d orbitals, s and p can hold another 8. So the total works out to be 18. So that's the origin of the 18 electron rule. You should not have any difficulty in understanding this, but I have repeated it here so that you are very clear about it. Next comes the question, why bother about electron counting? Is it really important? It's a very good guide to stability of a molecule in organometallic chemistry. So when you write a reaction with different intermediates, you can understand the stability of the intermediate by doing electron counting. So I would expect you to do electron counting.
Sir, your video is paused.
Okay. Let me PowerPoint slideshow. Yeah. So are you able to see my screen now?
Yes, sir. Yes, sir.
Okay, fine. So I have rejoined. This is carbon monoxide, something that we will be dealing with. Carbon monoxide has got lone pairs, one on the oxygen side, one on the carbon side. A carbene, for example, has also got a lone pair.
Hello, sir. Excuse me, sir.
Yes.
Sir, we weren't able to see the slides from previous slide. From the previous slide onwards, we weren't able to see your video.
Are you able to see it now?
Yes, sir. It is clear now, but from the previous slide onwards, your video was stuck.
Okay.
Stability of intermediates. After that, I couldn't hear or see anything.
So, were you able to see this with why bother with electron counting?
Like
Yes,
just the first 2 points.
Okay. So, after that, I only told you that for any catalytic cycle, you would have to write the intermediates, and it is helpful to do the electron counting for each of the intermediates so that you know whether the intermediate is going to be reasonably stable or not. And usually in a catalytic cycle, the catalyst is regenerated. Okay, so you need to write it out in such a way that you go through oxidation state changes with a proper increase and decrease in electron counts. So the final electron count of the catalyst should be the same as the initial electron count of the catalyst. That's what I mentioned. Okay. So now the neutral electron counts, water, ammonia, phosphine, they are all Lewis bases. They are 2 electron donors. And there are other molecules like unusual molecules like carbenes. In fact, carbon monoxide is very similar to a carbene. And isocyanide is also an unusual molecule, Rn triple bond C. That's one way to write it. You would write it as, if you write it with a triple bond, then you do have a coordinate covalent type of interaction. You can also write it with Rn double bond C. Then also you end up with a lone pair on the carbon. An alkene is not a Lewis base, but it has got a set of pi electrons. It has got a set of pi electrons which are concentrated on the carbon-carbon double bond, and on both sides of the olefin there is a region of electron density that can be donated to the metal. So the pi electrons, there are 2 of them, and they are spread on either side of the olefin. They can be used as if it's like a Lewis base. So a rule of thumb is that all these molecules donate a pair of electrons. So they are 2 electron donors. When you come to dienes and arenes, it's very easy to see that a diene has got 2 double bonds. So 2 electrons can come from here, and 2 electrons can come from here. So this is a total of a 4 electron donor. Similarly, an arene can have 6 pi electrons. So an arene can have 6 pi electrons. You have to just draw it in a localized fashion in order to see the fact that it is equivalent to 3 alkenes. So these are simple neutral donor ligands. There is no charge in them. Whereas we have in our repository several ligands like halides. Okay, halides are usually taken as negatively charged ligands, and they have a total of 8 valence electrons. They have a total of 8 valence electrons, but when they approach a metal, it is only this one pair of electrons that is donated to the metal. We assume that it is a 2-electron donor. There are reasons to suspect this because there are situations where a chloride, for example, can use this extra pair of electrons that are there. This pair of electrons. Why not use this also? It is true that this will be in a pi fashion, whereas this is a sigma donation, but nevertheless it can donate more than 2 electrons. But nevertheless, for electron counting purposes in organometallic compounds, the halides are considered as 2-electron donors. They are simple 2-electron donors. Similarly, cyanide, that's easy to see, Cn minus, is also a donor. It is isoelectronic with carbon monoxide, so it's very easy to see where the 2 electrons is coming from. It's coming from the carbon end, and it can be donated to a metal as a 2-electron donor. Alkyl groups and aryl groups need a little bit of explanation. In general, carbon is more electronegative. The electronegativity of carbon is greater than the electronegativity of the metal. Because the average electronegativity of a metal is less than the electronegativity of carbon, we take alkyl groups as negatively charged. So if I take CH3 as a group, it has originally a single electron next to the methyl group, but when it approaches the metal, we assume that because the electronegativity is larger than that of the metal will lose the electron completely, and this will become CH3 minus. And so also any other group that is approaching the metal, let's say this is a C5H5 radical, C5H5 radical. It has got one electron in that radical orbital, but then when it comes close to a metal, it grabs another electron from the metal and it acquires an additional electron, and so it becomes C6H5 minus. So we consider all of them as having 2 electrons, and they are all 2-electron donors. A hydride, for the same reason, is H dot, but then when it is attached to an M, we call it a metal hydride, by which we mean H is H minus. 2 electrons are there. In general, draw the Lewis dot structure for any molecule that you want to discuss. Any molecule that you want to discuss, you draw a Lewis dot structure, and then the Lewis dot structure will tell you whether you have an extra pair of electrons or not. For example, if I take BH3, I know that the Lewis dot structure of BH3 has got no extra pair of electrons. So this cannot be a good ligand. This is not a good ligand. Now, when you go to 3-atom and 5-atom systems, we do a similar jugglery as far as allyl groups are concerned. For the allyl group, we consider that as allyl minus, and so we consider that as a 4-electron donor. The allyl group can also be a 2-electron donor if the double bond is not interacting. So the allyl group is a bit ambivalent. It can either be a 2-electron donor or 4-electron donor, depending on the distance between the metal and the 3 carbons. If they are equidistant, then we consider it as a 4-electron donor. If, for example, the metal is far away from the double bond, then it is a 2-electron donor. Similarly, a cyclopentadienyl anion is a 6-electron donor because this would be considered as C5H5 minus. You can recognize that this is an aromatic system. It has got 6 pi electrons, 2 from the anion that we have generated by taking in an extra electron into the C5H5 pi system. So you have a total of 6 electrons that you can donate from the, if you write a valence bond structure again, you can see this readily. So you have 2 electrons from here, 2 electrons from here, 2 electrons from here, and so you have 6 electrons. So all this is fairly readily understood. The simplest way is to, for a pi electron system, you just count the number of carbon atoms. If n is even, it is 2n. The number of electrons that are being given, sorry, if n is even, number of electrons equals the number of carbons. So C4H6, which is butadiene, C4H6, which is butadiene, you would consider it as a 4-electron donor because there are 4 carbons. If I have 5 carbons, like we just discussed, you have to add 1 electron in the anionic or the ionic method. So we are talking about the ionic method of counting electrons, electron counting, and this is a bit strange sometimes because the metal can be more electronegative than the group carbon or hydrogen. And I will show you electronegativity is basically the ability of a metal to pull electrons to itself. So when you have the ability to pull electrons to yourself, it depends on other groups which are present. If I have fluoride attached to a carbon, then the CF group pulls electrons more effectively towards itself than a CH group. So similarly, a metal which has got very electron withdrawing groups attached to itself can be very electronegative, more electronegative than carbon. As a result, the simple-minded way of counting electrons could be a bit strange. We will come to examples as we go along. But in general, the ionic way of counting electrons is reasonably good. It gives us an idea about the nature of the metal and its characteristic. So let's try a few examples. Cp2TiCl2. This is a neutral molecule. And it's very important to know the charge on the molecule before we do electron counting. We will come to handling charge systems. Cp2TiCl2. Cp will give 6 electrons and it has a negative charge. Cl will give 2 electrons. 2 chlorines are there, so 2 negative charges are there. Totally, we have a charge, a negative charge from the ligands, which is equal to -4. And because the ligands have a -4 charge, the titanium must be +4. If this whole system has to be neutral, titanium has to be +4. So if titanium is +4, then obviously the metal is not giving any electrons to the system. So just hold on for a second. So what is happening is gives 0 electrons. Zero electrons are given by this. The ligands are giving a total of 2 into 6 from the CP, 12 electrons, and 2 into 2, 4 electrons, and we get a total of 16 valence electrons. So in principle, CP2TiCl2 does not have an 18 electron structure. It can accommodate another Lewis base. I have chosen this example just so that you realize that not all organometallic compounds have a valence count of 18, although most of them have. Having less than 18 is not a problem. Having more than 18 is a serious problem. Whereas in coordination chemistry, you can have more than 18. That is the major difference that you have between organometallic chemistry and coordination chemistry. So ligands can be ionic or neutral. The number of electrons donated to the metal, if the metal is A, and the electrons contributed by the metal is B, if you take the ligands to be contributing A and the metal to be contributing B, A plus B is the total valence electron count, and that's what we saw here. B in this case was 0 in the previous example. But if I have a charge on the net charge on the molecule, then I should subtract electrons if I have a plus charge. I should add electrons if I have a negative charge. That's the only difference between a charge complex and a neutral complex. Now let me proceed to the second method, which is the neutral method. The neutral method suggests, this is proposed not too long ago in by several fairly influential people, and it's called the covalent bond classification method. Covalent bond classification method, CBC. And you will find this, there is a website which has been devoted to it, and there are several articles, and I will post one of the articles today for you to read. All this tells you why you should follow the neutral method rather than the ionic method. But the net electron count does not change. So I will not worry whether you use the ionic method or the neutral method. But whatever method you use, you have to be consistent. You cannot change your method as the time goes along. I mean, within a problem. When you're doing a problem, you can use either the ionic method or the neutral method. So in the neutral method, irrespective of what ligands are around the metal contributes all the d electrons. So it is always considered to be a neutral species. You ignore the oxidation state concept. And similarly, you do the same thing for the ligands. And if, for example, you have fluorine, you know very well that fluoride is extremely electronegative and it will grab whatever electron density there is around. But still, you take fluoride as a neutral molecule, neutral species, and you consider it as a 1 electron donor. This is a very strange thing, but this is the way the neutral or the covalent bond classification method suggests that we do electron counting. The net charge, so all you have to do is to count all the electrons that will be involved in the bonding, all the electrons on the metal A, plus all the electrons that are in the ligand which are pointed towards the metal, and you count everything A plus B, and then you look at the net charge. If the net charge is negative, you add electrons. If the net charge is positive, you subtract electrons. So A plus B minus C is the total valence electron count. So this valence electron count is A plus B minus C. So when you have a positive charge, you have to subtract. That is why this minus sign is coming. So if you have a negative charge, then you add that number of electrons. So let's take a look at the some of the examples. But let's write out Cp2TiCl2. Chlorine is a halogen. It's considered as a neutral species, so it is Cl dot. So Cl dot is a 1 electron donor. Similarly, Cp is again a 5 electron donor. Titanium is a 4 electron donor. Even if titanium had fluorines, you would still consider titanium as a titanium 0 species. Even if it was Cp2TiF2, you would consider that as a 4 electron donor. So 4 electrons plus 2 into 5 from Cp plus 2 into 1 . So that's how we get our 16 electrons. This is 10 plus 2, 12 plus 4, 16 electrons. So the result of the neutral method and the ionic method is exactly the same. The same result is obtained whether you use the neutral method or the ionic method. So let's go to a table where I have listed for you all the ligands. And I have to quickly rush through this now. This is the ionic method. This is the neutral method. So you do not have any difference when you come to Lewis basis, simple Lewis basis. You have the same number of electrons which are donated, whether you have the ionic method or the neutral method. Similarly, for example, here, you have the same number. You do not have any change. There are a few cases where life becomes very difficult. And this is in the case of nitric oxide. So I will deal with nitric oxide in a detailed fashion. We may not have time today, but we will do that in the next class. But all the other cases, I think you should be able to go back and read this section again and be able to do electron counting in a fairly facile way. on the fly. That means as I talk, you should be able to do it. Okay. Now what I'm going to do is to okay, this is a summary slide. This is the same as what we just talked about. Now let me just summarize by saying that method A, you have a formal oxidation state, and so the electronegativity of the ligand is used to determine whether you have ionic system or you do not have an ionic system. So you just use the electronegativity method in order to count the electrons or count the ligand as an anion or a radical. Whereas the neutral method just ignores the formal oxidation state. So you just do not think about whether it's fluoride or carbon or hydrogen, it doesn't matter. You just assume that everything is neutral. So that's why they call it the covalent bond classification. But the end result should be the same, whichever way you count electrons. Okay, let's now do a small quiz. And to do the quiz, I think I have to, I will turn off the, sharing screen, and let me give you a small test in the remaining few minutes. So this is about okay, just hold on for a second. I will have okay, so I will show you the screen where I have shared this. This is, go to this website www.kahoot.it. I'm sorry, I think I said 80. It is www.it, and the game pin is 9142290. So you go to this website and type in this number. You should be able to see a screen where you can join the game. Okay. So you'll have to log in.
Excuse me, sir.
Yes.
Sir, I am not on the team, so can I also participate there, because I have not mailed you till now.
Tell me again, I didn't hear you.
Sir,
You can.
I am not added in the Teams account.
Sure. Anybody can join. Anybody can join. So since this is the first time we are doing it, I am waiting for. So I presume that only 7 of you are paying attention. Okay. Okay, so there are 15 people now in the game. People who join late can join. I'm going to join myself. Okay, so so this is just for me to check to make sure that things are all right. I'm going to start the game, right? So click on whichever one that you think is the right answer, and you should be.
Sir?
Yes.
So in my screen, it just shows the shapes. There's no option.
Go down below, move the screen a little bit, and yeah, there is only the color that you're seeing. Is that right?
Sir. Yes, sir, only the colors. There's no question and no option.
So, okay. So,
hello, sir. For my
Yes,
case,
sir.
this is
My case
also the case.
Okay, but are you able to see the screen that I am sharing here?
Yes, sir.
Yes, sir. No, yes.
Okay, so there is a problem.
There's no question as well in our screen.
Okay, okay, fine. So I'll have to check this. Let's try one more. Okay, are you not able to see the answers again?
So there's no question or answer.
There is no question.
We have to look at your screen.
Okay, okay, fine. I think there is a problem. So this is good. But are you able to see my screen though?
Yes, sir. We can see the question and answers in your screen.
On your screen.
In the screen. Okay, fine. So we'll have to figure out how we can have it on your device. You should be able to see the question and the answer, right? So let me see. So I will end the game here. So I'll just end the game. And let's try. Let's try one more. And then okay. If I okay. So now the number is 6227401. Let's try this. After that, I will good. This time, all of you have okay. So I'm just going to start. Let's just try it. If it doesn't work, then I will have to. Yes. Now, what do you see? You're not able to see on your screen, right?
Yes, sir. There is
same problem is there. Okay, so I have checked it in my screen also. So I understand the problem. We are only able to see it on the shared screen that I am showing you. So you need two screens in order to play the game, which is not very convenient. So I will try to fix this problem and then get back to you, right? So let's stop here. So let's stop here and let me go to go back to the PowerPoint. and I will find out how to do this without having this difficulty, right? So let me share the PowerPoint again. Okay, so okay, so in the remaining few minutes, I will just show you three examples where we have done electron counting in the two different methods, and then Friday I will deal with problem ligands. So here I have ClMnCO5. This is ClMnCO5, and this is the ionic method, the first one that I did, and this is the neutral method. Now, I also need you to remember the electron counts on the metal. So I have shared a periodic table in the files page. So you can keep that in a convenient place for you to look up during the class. That's not a problem. Manganese has D5S2 configuration. So a total of 7 electrons are there, right? So let's do the neutral method first. Manganese has 7 electrons. Chlorine contributes only 1 electron. It's the neutral method. So carbon monoxide contributes 2 electrons each. 5 of them are there, so 10 electrons. So if you add up, then you end up with 18 electrons for ClMnCO5. When I do the same electron counting with the ionic method, Cl is Cl minus. It's more electronegative than the manganese. So we consider that as Cl minus. So because the net charge is zero, manganese must be manganese plus 1, because all other ligands are neutral. So as a result, this is plus 1, this is minus 1, the net charge will be 0. So if it is plus 1, it can contribute only 6 electrons because it has lost 1 electron. Cl is Cl minus, so it contributes 2 electrons. Total of 18 electrons again. So it's 18 electrons whether you count it by the neutral method, or 18 whether you count it by the ionic method. Ferrocene, similarly, you end up with 6 electrons on the iron for the ionic method, because C5H5 minus is the ionic form of the ligand Cp. Cp is C5H5 and it is Cp minus in the ionic method. So it contributes 6 electrons each. So into 2 will be 12 electrons, and iron, because it is the net charge is 0 on the ferrocene, you have plus 2 charge on the iron. Plus 2 charge on the iron leaves it with 6 electrons on the valence shell. So 6 electrons in the valence shell plus 12 electrons for the Cp gives you again an electron count of 18. Same molecule for the ferrocene, you end up with 18 because you have iron 8 and C5H5 is now neutral and you have 10 electrons each. So what we have seen today, I'll have to stop here because it's going to be 10 o'clock. What we have seen here is 2 different methods of electron counting, the ionic method and the neutral method. And I would like you to brush up on these aspects. I will give you a better form of a quiz next time and have some more participation. Thank you very much. Any questions we can take? Otherwise, you're dispersed. You can leave the class.
Excuse me, sir.
Yes.
Sir, for adding into the teams, we have to mail you.
Yes.
Okay.
Or you can also, there is a place where you can request for joining in the Teams itself. There is a way to request. You just click on IP312 and say, I want to join. But you can send me an email. That's a simple method.
Okay, sir.
Anybody else? Any question? Otherwise, we can stop here for today.
Sir, regarding taking off notes.
Sorry?
Sir, regarding taking off notes on the Microsoft Teams. I mean, class notebook on the Microsoft Teams.
Yes.
So we won't be. I mean, it's difficult to type down the compounds, right? So in that case, do we just need to?
So what I suggest is, because we are having a chemistry class, what I suggest is you take it on a sheet of paper. You can just take a snap of it and upload it on the class notebook. The class notebook will allow you to upload any JPEG file, Excel file, doc file, PNG file, any file can be uploaded onto the class notebook.
Okay, thank you.
Any other question?
Sir, while discussing the definition of hapticity, the carbon atom should be continuous, right? The donating carbon atoms. I'm saying that we have, say, a double bond at one side and a negative at another side, negative charge on a carbon, like they are not continuous. Then they would be considered eta 2 and eta 1 separately, right?
Yeah, but the carbons are connected, right? So it's very difficult to count like that. It's not counted. See, it is a contiguous pi system.
Okay.
I wrote the Lewis structure only to help you understand, count the electrons. So hapticity comes from the number of carbons which are connected to the metal through a bond. Okay, so let me write and show you. This is your question. So it's not as if it's donating 2 electrons here and then the same to the same metal, another independent 2 electrons are contributed by the allyl radical, okay, or allyl anion. So we cannot consider them independently because this is a contiguous pi system. So you would consider it as eta 3.
Now I'm saying if there is another carbon in between the anionic carbon and the double bond, which is not in conjugation, then it will be considered separate, right?
Yes. You're talking about something like this. Yeah. No, this also becomes a continuous system. What you're talking about is maybe...
yes, sir, this one.
Maybe this.
Yeah.
Then it would be eta 2, eta 2.
Eta 2, eta 2, right? Not eta 4.
No, it's not.
Okay.
This is not eta 4.
Okay, thank
you. Nomenclature is something that you should have a rough idea about, but many times I'm not. I think nowadays it's easy to get nomenclature generated even. So I'm not particularly teaching nomenclature in the class. Okay, so if there are no other questions, I will stop my class now. Thank you very much.
Thank you, sir.
Yeah, bye.
Thank you, sir.
Yeah.